am Lakshmi Prasanna, Assistant Professor, Department of ECE, Institute of Aeronautical Engineering. In this session, we will discuss about memory interfacing to 8086 microprocessor. So here, the memory can be either static RAM and EPROM. So before going to the discussion of how to interface memory to 8086 microprocessor, we will see some small introduction regarding memory interfacing. So in this semiconductor memory interfacing, what is the main purpose of learning about this memory and interfacing this memory to 8086 microprocessor means? So in the design of all computers, here semiconductor memories are very useful as a primary storage for data and program. So that means here all these memories are the storage devices where this program and data can be stored. So by using this or accessing these memories only, the CPU can access all these programs and data. And so these memories can be directly connected to the CPU and they are the memory that the CPU asks for the information. So the CPU will ask the information regarding program or data to the memory only. And so here among different types of memories, mostly used memories are here RAM and ROM. So here RAM stands for random access memory and ROM stands for read-only memory. So we should know what is meant by memory capacity. So here memory capacity means the number of bits the semiconductor memory chip can store is called as memory. So here the number of bits we are saying, okay, so it may be either bits or bytes. How much amount of data the memory can store? It says the memory capacity. And so coming to here, the memory organization. So before going to this concept, we should recall some of the features of 8086 microprocessor. That is, 8086 microprocessor consists of 20 address lines, that is from A0 to A19, and it consists of 16 data lines, that is from D0 to D50. Now, so each memory chip contains locations. Here locations will be indicated with a variable n. So here the variable n represents the number of address lines that are related to the chip. And next, coming to the number of data lines, how it will be represented means each location contains y number of bits. So the variable y here, it indicates the number of data pins that are connected to the chip. So here n represents the number of address lines, whereas here y represents the number of data lines. So generally, whatever the size of the memory chip is, we have to write that size of the memory chip in terms of 2 power n by y. And where this n value represents the number of address lines. So for example, here if the memory organization that is given is 4K by 4. So in order to indicate this value of 4K, we have to write that 4K value in terms of 2 power n, where n represents the number of address lines. Okay. So as we know here, the value of 2 power 10 is 1K. Okay. So the value of 2 power 11 is 2K. So similarly, so the value of 2 power 12 is 4K. So 2 power 13 is 8K. So similarly here 2 power 15 and here first 2 power 14 next. So here 2 power 14 value, it is 16K. So like that, we have to write 2 power 15 as 32K and 2 power 16 as 64K. So we have to represent the value of the size of the IC in terms of 2 power n. So where n represents the number of address lines. So here the chip size is 4K. So the 4K value is here 2 power 12. So the value of 4K, it represents there are 4096 locations. It should be written in terms of 2 power 12. So here this 12 represents the number of address lines. Okay. So each location will be holding 4 bits. Now, so coming to the semiconductor RAMs, that is random access memory. These RAMs are classified into 2 types. Here the 2 types are, one is static RAM. So it can be simply represented as SRAM. Another one is dynamic RAM. So it can be simply represented as DRAM. Okay. So SRAM represents static RAM and DRAM represents dynamic RAM. So these are the main 2 categories of the semiconductor RAMs. Now, so coming to some of the differences between this static RAM and dynamic RAM. So here in the static RAM, transistors are used to store the information in SRAM, whereas in the dynamic RAM, capacitors will be used to store the data in the dynamic RAM. And coming to the next difference, in the static RAM, capacitors are not used. So that is the reason refreshing is required every time. And whereas in the dynamic RAM, to store the information for a longer time, so the contents of the capacitor needs to be refreshed periodically, regularly. And so static RAM is faster compared to the dynamic RAM. So dynamic RAM provides slower access. That means the speed of the DRAM is slow. And static RAMs are very expensive because we need to use this transistors for the storage. And whereas in the DRAM, they are low cost because here only capacitors will be used to store the data. And coming to SRAM, SRAMs are low density devices, whereas DRAMs are high density devices because more number of capacitors will be used in this case to store the data. And so static RAMs will be used in the cache memories, whereas dynamic RAMs will be used in the main memories. So these are some of the differences between static RAM and dynamic RAM. Now, so here, as we know, in 8086 microprocessor, it consists of 16 data lines and 20 address lines. How all these things can be arranged? So if we consider the memory chips, they have to access this 16-bit data bus. So this 16 bits will be divided into 8 plus 8. Okay. So here the 16 bits 8 plus 8 means the upper 8-bit bank is called as odd address, whereas the lower 8-bit bank will be called as even address memory bank. So here the totally the 16-bit data bus width will be divided into 2 8-bits. Okay. So the upper 8 bits will be related to this odd address memory bank and the lower 8 bits will be related to the even address memory bank. And so after dividing this 16 data bits into 8 upper and 8 lower to address even and odd banks, next we have to connect the availability memory address lines of the memory chips. And also we have to connect the 2 signals called RD bar and WR bar. So here RD bar indicates read and WR bar indicates write. So these 2 signals should be connected to the microprocessor. And So then connect the 16-bit data bus of the memory bank with 8086 microprocessor. And so after considering this read and write signals and connecting the two memories to 8086 microprocessor, next we have to consider this BHE bar and A0 signals of 8086 microprocessor. So while studying the pin configuration, this A0 and BHE bar, these are the two signals which will decide either it is a byte data transfer or word data transfer. If it is byte, either it is lower byte or higher byte. Okay, so all these things will be decided by these two signals, BHE bar and A0 signals of 8086 microprocessor. So you have to consider these two signals in order to decode. And so select the signals of odd and even address bank. The chip select of the memory will be driven from the output of the decoding circuit. So you have to consider this procedure in order to do the memory mapping. And so following that procedure, we will solve two examples related to semiconductor memory interfacing, and we will draw the interfacing diagram how to interface memory to 8086 microprocessor. And so here this is the example given. So here they are asking interface two 4K by 8 EPROMs and two 4K by 8 RAM chips with 8086 microprocessor. Okay. So here, as we know, the memory size of 8086 microprocessor, that is physical memory size of 8086 microprocessor is 1 MB. Okay. So among this 1 MB, to make the address space continuous, we will follow the given procedure. So what is the given procedure means here? First we have to consider the size of the memory. That memory size we have to write in terms of 2 power n. So it says how many number of address lines it should be used. Okay, so this procedure we have to follow. And so after reset, the IP and CS will be initialized to FFF0H. So we must first calculate the total number of address lines required for 8 kilobytes of EPROM. Okay, so the number of address lines will be 13. So how you will get means, see here first two 4K by 8 ROMs are there. Okay, so 4K, it is 2 number. So here 4K into 2. So we are getting here the value 8K. So here what is the value of 8K? You have to write the value of 8K in terms of 2 power. So the value of 8K in terms of 2 power is 13. Okay, so the value of 2 power 13 is 8K. So this 13 is n. Okay, so this n value represents the number of address lines. So this n value represents the number of address lines. Okay, and so similarly in this case also two 4K by 8 RAM chips. Okay, so in this case also if you see 4K by 2. So what is this 2 means? Here the number of 4K by 8 ROM chips are 2. So totally here we are going to get the value 8K. Okay, so for this RAM also 8K, it can be written in terms of 2 power 13. For this also the number of address lines are 13. Okay, so in both the cases we have concluded that the number of address lines required are 13. Okay, so the number of address lines are 13. So in order to indicate this, it will be from A0 to A12. So we have to use the address lines to do memory mapping only from A0 to A12 in both ROM and RAM. Now, so this is the table we have to consider. So since there the number of address lines we have got is 13. So it represents A0 to 12 address lines only should be used. So if you see here, but total number of address lines available in 8086 microprocessor is 20. So it will be from A0 to A19. But among the 20 address lines, based on the size of the chip, it is decided that only 13 address lines should be used. Okay. So here, this is the area which is related to ROM, and this is the table which is related to RAM. Okay. So if we consider here the starting address, here only 13 address lines should be used, that is from A0 to A12. Now, so A0 bit coming to ROM, here it is decided as the starting address, all zeros, and maximum address, that is ending address, will be all ones. And so here, coming to the RAM also wants 13 address lines only. So we have to use the address lines from A0 to A12. So starting address of the RAM will be here, this is the start address and this is the end address. And similarly here, this is the start address and this is the end address for RAM. And so here, this is the starting address. The starting address will be minimum address, it is 0. Whereas the maximum address, it will be 1. So this is the A12 bit. Up to A12 bit, it indicates the starting and ending address of the ROM and RAM. Next, so coming to the A13 bit, since the sizes of both the chips, that is ROM and RAM, both are equal. So in order to differentiate ROM and RAM, we are using here with the help of A13 bit. So in the A13 bit, in order to represent that it is ROM, we are keeping all these bits as 1. So in order to say that it is RAM, we are differentiating that by keeping this A13 bit with 0. Okay. And so here, the remaining address lines are not used. Based on the size of the chip, only 13 lines are used. This A13th bit is used to differentiate ROM and RAM to indicate 0 and 1. And from bits A14 to A19 are not used. So all of them will be kept as high, that is 1. Why? Because here, this is the A13 bit common to both ROM and RAM. Sizes of the chips are equal. So we need to select or we need to use a decoder in the address mapping, memory mapping. So in order to select the decoder and all, we have to see that all the bits from A14 to A19 should be high. So after making all this, you have to write what is the starting address and ending address of the ROM and RAM. So here if you see 1111, it is F, and 1110, it is E, and all these are zeros. So the remaining value is 0. So that is the starting address of the ROM. And next one is, if you see here, all these are 4 ones. All these are 4 ones. So all are ones. So the ending address of this ROM will be all F. And coming to RAM here all the starting address 4 bits are ones. So the value is F. And next 1100, the value will be C. And remaining bits are zeros. So the value will be 000. So to decide the ending address of the RAM, here this is the ending address. All these 4 bits are 1. And this is F here. And 1101, the value is D. And all remaining are 1. So it will be FFF. So like this, we have to find the starting address and ending address of ROM and RAM. Next. So along with this number of address lines, next we should also take the consideration into A0 and BHE bar signal. So this A0 and BHE bar signal decides whether it has to transfer word or whether it has to transfer byte. So if it is byte, whether it is lower address byte or higher address byte. Okay. And here this is the A13 bit. If this A13 bit is kept as 0, see, if this A13 bit is kept as 0, it will be indicated as RAM. So if this is 0, it will be indicated as RAM. If this A13 bit is indicated as 1, A13 bit is indicated as 1, it will be considered as ROM. So it will be considered as ROM. So this A13 bit will decide whether RAM or ROM. This A0 and BHE bar will decide whether word transfer or byte transfer. If it is byte transfer, whether it is lower byte or higher byte. So if this A0 and BHE both are zeros, so word transfer. So here word transfer means totally 16 bits. So it is considered as both even and odd address. So if it is 0, 1, byte transfer, that to lower byte D0 to D7. So here lower byte means it will be indicated as even address. And D8 to D15, it is called upper byte. So if it is upper byte, it will be called as odd address. So similarly for ROM, so if you consider here, there is no combination 1, 1. Okay, so we have learned in the pin configuration of 8086 also, there is no such combination like A0 and BHE bar both ones. Why? Because if both are ones, the combination is invalid. Okay, so only it will be 0, 0, 0, 1, 1, 0. There will not be 1, 1 combination. So similarly in case of this ROM also, if it is 0, 0, both even and odd because it is word selection. If it is 0, 1, only lower byte, so it is considered as even address. If it is 1, 0, it is considered as higher address. That means only odd address of the ROM. Okay. So based on this table and the combination of these bits, we are going to draw the interfacing diagram. So here, this is the interfacing diagram we can observe. And we are here interfacing with the help of this 3 to 8 decoder. Okay. So here we are going to take the help of this 3 to 8 decoder because it consists of 3 inputs. So all these are the 3 inputs, A0 and BHE bar. Along with that, this is A13 bit which will be deciding ROM and RAM. So those are the 3 inputs. And the output of this 3 to 8 decoder circuit consists of 8 outputs. The 8 outputs are O0 to O7. So these outputs will be driving all these chips. And so here in this problem, based on the size of the chip, we know that only 13 address lines are used. 13 address lines are used. Okay. But 8086 microprocessor consists of 20 address lines. Okay. So if it is 13 address lines used, that is from A0 to A12, the bits from A13 to A19 are not used. Okay. So here the bits from A13 to A19 will be used in order to select the decoder circuit. So 13th bit will not be there. Okay. Why? Because it is taken to differentiate ROM and RAM by indicating 0 and 1. So the bits from A14 to A19 will be used in order to select this decoder circuit. Okay. So if this A0, A13 and BHE bar, both 3 signals are 0, this O0 signal will be selected. If it is 0, 0, 1, this O1 signal will be selected. So similarly, we can see here the table. So this is 0, 0, 0, the value is 0. So this is 0, 0, 1, it represents the value 1. This is 0, 1, 0, it represents the value 2. And here, this is 1, 0, 0, the value is 4. 1, 0, 1, the value is 5. 1, 1, 0, the value is 6. Okay. So here there is no combination like 3 and 7 because that combination is invalid. So if you are going for this ROM, we have to use 0, 1 and 2 signals only. Okay, so that is why here 0, 1 and 2 signals only are taken when RAM is used. So this is the RAM IC. Okay, so here 0 is common. Why? Because it is meant for word transfer, that is both even address and odd address. So if you see here, if it is 0 both even and odd address, so it will be common to both the ICs. But whereas if you consider this 1 and 2, here 1 is for even address and 2 is for odd address. Okay, so that is here 1 it is for even address and 2 it is for odd address. So that is why here even address means RAM. So this is the even chip, 8 bits, lower 8 bits, D0 to D7, and this is odd of RAM, higher 8 bits, upper 8 bits, that is D8 to D15. So the chip selection logic for this odd, here you can see this is CS3 bar. So this is the CS3 bar signal that should be interfaced to this RAM. And here you can observe CS4 in order to select the even. So this even will be connected to the CS4 chip selection logic of this RAM 4K by 8. And we can see here this is up to 12, that is 13 address lines will be used. And similarly here, if you see, these are the ICs related to RAM. And coming to ROM here, when the ROM is selected here, okay, so we are using 4, 5 and 6. Okay, so 4 means it is common to both the even and odd. So that is why 4 will be common to both the even and odd. Whereas here 5 will be indicating the even. So 5 will be indicating even, whereas 6 will be indicating odd. Okay, so that is why. So this is the odd address bank and this is the even address bank. Okay, so using this 4 and 6 odd, so it is going to drive this CS1 bar chip of this 4K by 8 ROM, and for this CS2 bar chip, it is going to drive another one. Okay, so this is how we have to do the interfacing. So if you see here, if this 0 is selected, it represents this RAM will be operated because this 0 is the signal connected to the AND gates which are used for this RAM. So here if you see, ROM means read-only memory, only reading is possible. That is why only memory read signals will be connected here. But whereas if you consider RAM, both reading and writing is possible. So for this IC, both read and write signals will be there. Okay, so this is what we how we have to interface this two 4K by 8 EPROMs and two 4K by 8 RAM chips to 8086 microprocessor. Okay, so in this following example, since the two sizes of the chips are equal, we are getting this A13 bit as the common bit. Now we will see another example where we are getting different address bit for the two ICs. So since the 13th bit is same, we have taken help of the decoder to make the chip selection of the ICs. But here we will see without using the decoder circuit, because like A13th bit, here we cannot find any common bit. Here you have to design the interface between 8086 microprocessor. Here it is given two chips of 16K by 8 ROM and two chips of 32K by 8 RAM should be used. Okay, and the starting address of the EPROM should be selected suitably, whereas the RAM address should be starting from 000H. Okay, So following all these conditions, first we have to see here 16K by 8, 2 chips. Okay. So 16K by 2, here the value is 16 into 2, 32K. Okay. So we have to write the value 32K in terms of 2 power. So the value of 32K is 2 power 15. So where 15 represents the number of address lines. So here 15 is the number of address lines we have to use. That is from A0 to A14. Okay. So this is in case of ROM. Now, so whereas in case of RAM, if you consider, so there are 32K by 8 IC. That IC is also 2 ICs. So 32K by 2, we will get here 64K. So we have to write the 64K in terms of 2 power. That is 2 power 16 value. Okay. So it represents the number of address lines are 16. That is from A0 to A15. Okay. So previously both are A0 to A12 only because 13 address lines. But in this problem, since the sizes are different, you are getting different address lines. So here no need to use decoder, but the memory mapping will be done with the help of AND gates. Now, so taking that into consideration, same as the previous problem. So you have to consider the size of ROM and the size of RAM. Okay. So the size of ROM is here 32K and the size of the RAM is 64K. Okay. And so if you consider here ROM, what is the size of the address lines means? So in place of ROM, the size of the address lines is 15. So we have to use only from A0 to A14. So this is A0 and this is A14. Okay. And so by considering that, we have to write for ROM addresses. So this is the starting address where all will be zeros. And here this is the end address where all will be ones. And so this 14 bits. And what is the 15th bit here in case of ROM? It will decide the type of the memory. So if it is ROM, we will indicate that as 1. And coming to the RAM here it is 64K. Okay. So this is the starting address and this is the ending address. So in case of RAM, how many address lines are used here? So in case of RAM, the number of address lines are A0 to A15. So here A0 to A15. Okay. So this is what? A0 to A15. But whereas in the ROM, this is the last one. Okay. So here the starting address all will be zeros and ending address all will be ones. Now, so this is the 15th bit we have taken to indicate as 1 to say that it is ROM. But here up to 15 bits, it says the starting and ending address. But the maximum size is here 15. But here using this 16th bit, we are deciding the type of the memory. So if it is RAM, we have to indicate all that as zeros. Now, so since this is 1, we have to indicate all these ones. It is 0, so all these are indicated as zeros. But in the previous example, we have indicated all that as ones in order to enable the decoder. But here, since here we are getting in different bits, address lines, we are not going for decoder, we are using the AND gates. And so this is the semiconductor memory interfacing we have to refer. Okay. So in order to do that memory mapping. So based on the given data, so here there are two 16K by 8 and 16K by 8 ROM chips. And so here this is D0 to D7 lower order data lines. It indicates the even address and higher order data lines will be indicating the odd address. Similarly, we have here 32K by 8, 32K by 8 RAM even and odd. Okay. Now, so here In this case, the number of address lines what we have used, that is in ROM. So in ROM, the number of address lines we have used is 15. Okay, so ROM 15 we have used. So that is why here we have indicated A1 to A14. But here, whereas in the RAM, the number of address lines we have indicated is 16. So that is why here A1 to A15 address lines will be used. The number of address lines are 16. And so here previously in the example we have used the decoder circuit to select the chips here, like CS1, CS2, CS3 and CS4 we have used the decoder. But here in this example, since both the memory's address size is different, we are using here the AND gate. So here you can see A15 to A19 bits are used. Okay, so in order to go for ROM, and here A16 to A19 bits are used because this is related to RAM. Okay, so how you can decide whether it is RAM or ROM means, so here it is simply taken as C. It is C bar. Okay, and so if it is ROM, we are indicating the C bit as 1, and if it is RAM, we are indicating the C bit as 0, that is C dash. So that is why for RAM we will keep C dash. Okay, that is why we will say that the number of address lines, based on that we will say whether it is ROM or RAM. Now, so to what we have to connect this C bit, and to which two chips we have to connect this C bar means, C bar should be connected to the two chips of RAM, whereas the C should be connected to the two chips of ROM. Okay, and that too here, this is a C bit which will be saying one of the bit is related to ROM, and other two bits are A0 and BHE bar. And so this is the A0 which is active low, and this is also BHE bar which is active low. Okay, so if this is the case, CS is high, that means it is 1, this is 0, this is 1, this is 0. So if the combination of these are the bits, then this is going to drive the CH1, that is the odd address of the ROM chip. If this is CS2, it is going to drive the even address of CS2. Similarly here, this is the complement where RAM to indicate. So complement bit means it will be indicated with 0, and this is also the 0th bit, 0 and 0. If it is a combination, then this CS4 and CS3 bit chips will be selected such that it is able to drive the odd address and even address of the RAM chips. Okay, and so for the ROM, we can see here only read signal will be connected, whereas for this RAM, since both writing and reading is possible, we can see two signals will be connected. Okay, so like this, if we are getting the same address sizes, we have to go for decoder for memory mapping. If the addresses are different, like this, NAND gates can be used and we can do the memory mapping. So these are the two examples we can consider to understand how to do memory mapping for 8086 microprocessor and how to interface memory to 8086 microprocessor. Now, coming to dynamic RAM interfacing. So when we require large capacity of memory in a system, so the memory subsystem is generally designed using DRAM. So here DRAM can also be called as dynamic RAM. Okay, so if you want to store any large amount of memory in a system, we will consider dynamic RAM. Now, so we will see some of the advantages and disadvantages of this DRAM. So some of the advantages are, so high packing density, and it is of low cost and low power consumption. So these are the main advantages of using dynamic RAM. And so here the static RAM cell generally it is designed by using 6 transistors, whereas the dynamic RAM cell requires only 1 transistor. Along with the transistor, by using 1 capacitor, we can design this dynamic RAM. Okay, so static cell, RAM cell, in order to design, we require 6 transistors. But if we want to design the dynamic RAM, we can design by using only 1 transistor along with the capacitor. And so here are some of the disadvantages of dynamic RAM cell. So the disadvantages are, so the DRAM cell uses a capacitor. Okay, so why it is going to use the capacitor means in order to store the data. So how it is going to store means by charging that capacitor. Okay, so here the charge as the representation of data, but the reverse bias diode, what it will have means it will consist of leakage current. Okay, so that tends to discharge the capacitor, giving rise to the data loss. So because of this usage of capacitor in the DRAM, so leakage current will occur. So because of this leakage current, it is going to discharge. When the capacitor discharges, the data will be lost. So in order to avoid such problem, that is in order to avoid the data loss, we must refresh the DRAM cell after each fixed interval of time, so that the data loss can be avoided. So what are the precautions we have to take during refreshing of that DRAM cell for each fixed interval of time means? So during refreshing of this DRAM, the memory should do the following operations. Okay, so the IC will go such conditions like it is loss of time. So if you are going to refresh the DRAM cell every time at fixed interval of time, it is going to reduce the system performance. And so the refresh mechanisms and additional hardware requires make the interfacing of DRAM more complicated issue. So this is the main reason. That DRAM, in order to interface this DRAM memory to 8086 microprocessor, it requires additional hardware. So which leads to be more complicated for interfacing. So these are some of the disadvantages of using the dynamic RAM cell. And so coming to the dynamic RAM interfacing, so the refresh cycle, so as we have said, in order to avoid the data loss problems, we have to make the DRAM cell refresh every time for fixed interval of time. Okay, so the refresh cycle is different from the memory read cycle. Okay, so here these are the two things we are going to compare. That means how refresh cycle is happening and how this memory read cycle happens. So the memory address is not provided by the CPU. It is generated by a refresh mechanism counter, which is called as refresh counter. So when during the refresh cycle, the memory address for the CPU, the memory address, it is not provided by the microprocessor. It will be provided by the refresh mechanism. That means with the help of the refresh counter. And more than one memory chip may be enabled at a time. So what is the advantage if more than one memory chip enables? So it is going to reduce the number of total memory refresh cycles. Now, so here memory refresh is the independent regular activity initiated and carried out by the refresh mechanism. Okay, so in order to refresh this RAM cell, this refresh cycle is the general mechanism. And coming to another one, it is memory read cycle, whereas the memory read cycle is either initiated by external bus creator or a processor initiated operation. So here this refresh cycle or refreshing of the DRAM cell will be done with the help of this refresh mechanism, that is with the help of the refresh counter, whereas memory read operation will be initiated with the help of this external bus creator or a processor initiated operation. Now, so this is what about how to interface memory to 8086 microprocessor. Either it is SRAM or DRAM, if it is RAM, and also ROM. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.